Hi, I'm Chem's best friend. Today's video will be about chemical bonding. If you are interested in private tutoring lessons, the information is on the screen below me. All right, let's start. Today's lesson will be about chemical bonding, and let's look at my screen. Let's have a look at these objects that are right in front of us. Let's have a look here. Here is salt, seashells. Here I would like you to focus on there's sugar, caffeine, cinnamon, water. And here we have metals and alloys. These things have very different properties. You can burn sugar pretty easily. You cannot burn salt. Yet they both look like white crystals. So what's going on here? The key here is it's different bonding. They are made from different elements. Different types of bonding gives them very different properties. So let's explain. So here we have our periodic table, and we have blue area, which is our metals, and we have a red area, which is our non-metals. Let's ignore the green, which is metalloids, but you can clearly see the red step line that separates our metals from non-metals. And if we have blue and red, if I give you a bag of blue and red Lego blocks, and I ask you to build a house, you will be able to build 3 different types of houses. Let's think. Well, one house you can build is going to be a mix of blue and red blocks. Another house that you can build, house number 2, you can build only blue. And house number 3 will probably be will have to be, no other choice, all red. So remember, 3 different houses, mix, blue and red, or blue or all red. That's the same thing with how different elements can bond with each other. But let's go back for a second and think about why. Why do they want to bond like that? Remember, everything is explained that all the elements, they want to be stable. All the elements want to achieve a stability like a noble gas. They want to have their S and P orbitals filled. They want to have their octet filled. So they're going to gain or lose electrons to achieve that stability. The problem is who comes to the party, who shows up. They're going to do anything they can to achieve that stability. So let's go here. Let's write our notes. So there is 3 different bondings, remember? So first, we can have a blue and red. If we can have blue and red, we can have, the first possibility is we can have metal plus a non-metal bond. And that kind of bonding is ionic. We can also have the second house. Remember, our second house was blue and blue. So we can have a metal bonding with another metal. That's our metallic bonding. Metallic bonding. And the third combination is a non-metal with another non-metal. That was our red and red, our whole red house. And that will give us covalent bonding. Okay, let's go and explain this bonding a little more, and let's talk about properties. So first up will be our ionic bonding. So salts, here is seashells, are example of ionic bonding. So what's going on? So ionic bonding, they will form salts. So what's going on with ionic bonding? Well, we said that we have a metal plus a non-metal. Remember, a metal would like to lose electrons. So why does metal want to lose electrons? To achieve that stable noble gas configuration, to have S and P filled. And the non-metals, for them, they would like to gain electrons. It's easier for them to gain electrons than to lose. They would like to gain electrons. This is a great match. Think about it. This one wants to lose electrons, will then become a cation. So a positive charge. Someone wants to gain electrons, becomes anion. So what's going on? Here, there is this complete transfer of electrons. It's great. And then, when you have this complete transfer of electrons, what's going on? You have a cation and an anion, and they are attracted to each other. There is this nice attraction, yes? Coulomb's law, attraction. So we have a question, how does this bond stay together? That's the key. How does ionic bond stay together? Well, it's this electrostatic attraction between opposite charged ions. And this is the key for ionic bonding. They form these beautiful lattices. So they will not form, so you will not see one sodium ion and chloride ion walking together. But the smallest whole number ratio, the smallest is here 1:1, and we call the formula NaCl or table salt. I use this as an example. But you will never see one little building block on its own. You will see these beautiful lattices, big crystals. So let's talk about some properties of ionic compounds, of salts. Because you have this opposite attraction between opposite charged ion, this attraction is very strong. So it's very hard to break them. However, if we do, here's my ionic compound, and I'm going to hit it with a hammer. And when I hit a crystal of salt crystal with a hammer, what happens? It falls apart. Why does it fall apart? Well, let's look at the picture below. So I applied some stress, and look what happens here. Same charges are next to each other, and same charges next to each other repel. So this right here is a little problem, and it breaks apart. And crystals, you know, have these beautiful smooth edges. That's why, because you change the ionic, ions next to each other. So let's talk about some properties of salts. They are brittle. They have also extremely high melting points because this opposite charges attract so much. It will take a lot of energy to separate them. That's why you cannot melt salt. In order to melt ionic compounds, in order to melt salts, you have to go to 800 or a few thousands of degrees of Celsius. Very hard to melt them. So you cannot do that. And talking about melting, if you think about putting it into gas, it's even higher. So they are brittle. They have high melting points. High melting point. So like I'm going to say thousands of degrees. So that means that they are all solid at room temperature. They are all solid at room temperature. They have very high boiling points. They also dissolve in water because they are ions. Water molecules will attack them, and they dissolve in water, most of them. But I'm just going to say check your solubility rules, yes. And when they do dissolve in water, they will conduct electricity. Remember, in order to conduct electricity, you need to have two conditions. You need to have movement and charge. So when ions swim between water molecules, you have movement, and it's ions. So you have charge. So they will conduct electricity. Ionic compounds will also conduct electricity if you actually do melt them. So when melted, they will also conduct electricity because they will be movement and charge. Ions will be moving. So when you actually do melt them, they will also conduct electricity. However, they will not conduct electricity when they are in a solid form. So if you have a beaker with salt crystals, and you stick your 2 prongs in with a light bulb, the light bulb will not turn on. So here is some properties of ionic compounds. Let's move on. Next on our list was a combination of a blue and blue Lego blocks, a blue house. And for us, that will be symbolic as metal plus metal. So we have our metallic bonding. And they make, we call it metals. And it doesn't matter if it's a pure metal or an alloy. Pure gold, it's a metal. Stainless steel, alloy, it's a metal. Brass, it's a metal, we call it metal. So it's all metallic bonding. So what's going on? So they make from metal. So what's going on in metallic bonding? So we have a metal plus a metal. Remember, a metal wants to lose electrons. And this metal also would like to lose electrons. Well, we have a problem. Right? Before in ionic bonding, it was great. Something wanted to lose electrons, something wanted to gain electrons. It was easy problem to solve. Here, we have a different problem. We have both metals, and both would like to lose electrons. Why? Remember why? To have it octet filled, to be like a noble gas. So they would then like to here form a cation, and these guys would like to form a cation. But the problem is, where do the electrons go? Where do all valence, yes, do all valence then, valence electrons go? Well, the solution is going to have this. This is the solution. This is our metallic bonding. Going to come, we call it the sea of electrons model. Our sea of electrons model. And what's going on here is, I would like you to look, these are our valence electrons, these little dots, and these circles, these positive charges, they are not nuclei, they are our cations. So these are cations. So we have these cations, but then these cations have these electrons that are free floating between the cations. You can see the little purple dots. So how does this, what's going on? How does this bond stay together? Well, let's write this. The free floating electrons are attracted to all cations. And they can move between them. So the cations are not next to each other. So there is no repulsion because there is the electrons that can move. And this electron here, actually let's draw this. So this electron here is attracted to all the cations. It can move between all the cations. It is not stuck next to one of the cations. Okay, let's explore some properties of metals. So what happens when we hit a metal? Remember, when we hit a salt crystal, it broke, it shattered. What happens when you hit a metal? Well, it dents, right? It dents, it doesn't shatter. So metals, well, let's have a picture what's going on here. So here we have our metal and our cations and free-floating electrons, and we're going to hit it with a hammer, and we press it down, but then the cations just spread around and the electrons spread out around them, and we just made it a little flatter. So, wow. So that's the property of metals. They are malleable. And that means you can hit it and make it, you can hit it with, and it will not shatter. You can make it very thin sheets. Think of like aluminum foil. Malleable, they are ductile. What's ductile? You can form it into thin wires. So imagine here I have a flat surface. What if instead of a flat surface, I'm going to say I had a funnel. If I had a funnel here, I can keep hitting it with a hammer, and the cations will just go slowly and through to my funnel, and a wire will come out, right? So I can do that. So I can make them into that. So they are ductile. What else is going on? They are shiny. What's going on? Why are metals shiny? Well, hold on. I actually want my picture back quickly. There we go. So they are shiny. So what's going on? Well, if I hit a light, if a light hits my metal, the light hits a metal, and I have electrons on a surface, it gives it a little bit of energy, and all it happens is electrons just kind of skim on the surface of a cation, so they move a little bit. So the shiny that our eyes see as shiny is actually electrons moving. Electrons are floating on top of the cations, and they are moving. That's what gives metals the shine. So they are shiny. And what else happens? What else can metals do, which we use a lot? They conduct electricity. Because you have movement and charge. Electrons have charge and they are free to move. So metals are great at conducting electricity. Isn't this interesting? How now metals are different than ionic compounds, than crystals? Well, we have one more. Remember our red house, all red? The third combination was a nonmetal with a nonmetal, and that formed covalent bonding. Here we go. So we're going to go with our covalent bonding. And covalent bonding forms molecules. And molecules are small separate entities like you see here. Here is a glucose molecule. Glucose is part of sugar. So we have sugar here, we have caffeine in coffee, we have cinnamon. These are all separate molecules. They are all held together by covalent bonding. So we have our covalent bonding, and covalent bonding is, we have a nonmetal plus a nonmetal. So remember, nonmetals prefer to gain electrons. Wants to gain electrons, and nonmetal, this nonmetal wants to gain electrons. We have a problem. What's going on? So if there's not enough, people will say, well, share. So yes, so let's write this. We have a problem. There is not enough electrons. And what's the solution? We're going to share electrons. Okay, so let's explain. So let's say we have our fluorine coming with its 7 valence electrons. And remember, it has a spot for one more. It wants to have it one more, to have it octet filled, to get that stability, to at least pretend to be a noble gas, right? And we have another fluorine with its 7 valence electrons. So they say, hey, if this guy goes here and this electron goes here, we can then share them. So we will have something. So these ones will be shared. It looks like this. Right? So now this fluorine here, let's draw this. This fluorine here has 8 electrons around it. And this fluorine here has 8 electrons around it, yes? So here are my shared electrons, right here. These are my shared electrons. And this is my covalent bond. And now the question is, how does this bond stay together, right? That's why I want to explain. How does this bond stay together? Well, here is the key. The shared electrons are attracted to both nuclei. So let's write this. The shared electrons are attracted to both nuclei. And that's the key, how covalent bond stays together. Okay, let's explain some properties of our covalent compounds. So it's these molecules that are held together. And we have, if we have a sugar, we have many sugar molecules together. They're not held tightly. So they kind of have to, sugar molecules have to hold hands. And we will talk a different video about intermolecular forces. So because of that, they have very low melting points. You can melt sugar very easily. And then they have pretty low boiling points. Many actually molecular compounds already boiled away, like oxygen, O2, that's around us. It's gas at room temperature. So room temperature, it's already higher than its boiling point. It already boiled away. They are also not shiny. Not shiny, like sulfur, the yellow powder, it's not shiny. They are also, many of them are brittle. Sugar, think about sugar cubes. You can hit it with a hammer and also break them apart pretty easily. And they do not conduct electricity, except acids. But that's a different category. That was a topic of a different video. So they do not conduct electricity because there's no ions here. There's no ions that comes off anywhere and there's no movement. So they do not conduct electricity. And there we go. That was a little intro, an explanation of chemical bonding and different properties of different compounds. And hopefully you found it really interesting and enjoyed and learned something new. So thank you for watching and see you next time.